So hi everybody, thanks for coming, and I'll go to my slides. So I'm gonna kind of introduce everything I'm gonna do and then just kind of walk through as much of the code as we can get through. So my talk has to do with machine learning models where you're trying to predict something, and it's the effects of age on measurements of fairness of the models. So so I'm Valerie Carey. I have a background, a long time ago I worked in software quality control, writing automated tests for Solaris, if anyone knows what that is. I was a biophysics researcher for a while and a healthcare business analyst. And I'm a data scientist, been a data scientist for a while, but my current job is at Paychex. And I'm looking at client-facing applications that are related to the labor market. So we're predicting things related to, the hirings and firings and costs of employment and things like that. So
Are you doing anything with their indexing? Like I hear sometimes talked about Paychex is doing like index of how the economy is doing. Are you involved with that at all?
Only the littlest bit. Like one of Mike
Okay.
Nichols is the main one, but yeah, I've pulled a little bit of ERD data but mostly it's Mike Nichols, and he does a small business employment watch, things like that. But that's our group, But yeah, I'm doing more of like the client facing, meaning like Paychex does payroll. We have clients who are businesses, and then they log in and they can like see analytics for their employees and their business. So I'm responsible for building models, doing all the data cleaning, making sure the data is right. That's the biggest part of my job, and quality control, which includes fairness, because once we're in the labor market, making sure that we're not discriminating against people for whatever reason becomes very, very important. And I also blog, so this talk is related to one of my blog posts, which is actually I did for my work. It kind of is a personal project to understand my work better. So my Python journey. So I've been coming to this meetup off and on for I don't know, 5 years or something, but long gaps in there because mostly my work involves R. So nowadays I do half Python, half R, so I'm switching back and forth constantly. But I've never really formally learned Python, not even sort of like an online course. But I've used it, and certain classes I've taken. In my last job, I would automate SPSS, which was just a lot of file input and output sort of stuff done with Python. And now in my current job, I have to do it much more. We're using Azure, so we're kind of building our machine learning pipelines in Azure and connecting them up to other parts of Azure. So all of that is mostly Python based. And I do my sort of mini projects in Kaggle sometimes in Python. If you don't know, Kaggle's like a data science competition. So one of the reasons I want to give a talk today is, I mean, if I look at my like Python resume, and if I saw this, I would think this is pretty going to be pretty bad Python code. This is going to be not the best. Something done with this job title and learned in this context and kind of done here and there. It's not that good. So that's when I come to the meetup. I definitely want to improve. It's like I always do, just enough to get by. So any comments people have or tips, and hopefully I guess my goals today, I'm hoping that someone will, maybe I'll improve my coding, maybe even just having it subject to scrutiny will improve it a little bit. Hopefully I'll be able to give you something too. Like I'm going to demonstrate some libraries, especially related to pulling census data and visualizations. And some people may even be behind me in the Python curve, so maybe they'll learn something. So I'm talking about this blog post, which is called "Measuring Fairness When Ages Differ," which is posted on Towards Data Science. And so everything I'm going to talk about is out there. The code is on GitHub, and all my conclusions and my interpretation are all written up in this blog post, in case anyone's interested later. So those are the links, and I think they're in the meetup too. So if anyone's interested, so
Make sure that they're in the recording description as well.
Okay, cool, thank you. So I'm talking about fairness. So in the context of machine learning, what we want to do is we want to make sure if we're predicting something that is not introducing bias. Usually it's against gender, race, ethnicity, and age. Those would be major categories people measure fairness in. Here's this slide, just kind of shows a couple. You might have seen in the news, there were some controversies related to fairness of machine learning models. There was an accusation of sexism against the Apple Card, which I think recently an outside auditor has said, that has found no evidence of that. And also another article on the topic, but that was a big thing for Apple for a while, and Goldman Sachs. It was a very big controversy. The one on the right, ProPublica, wrote an article talking about racial bias and predictions of recidivism. So this is a very serious one because it occurs in jail sentencing. So they're looking at, their report is saying that certain error rates, the proportion of people whose whose determination of risk is incorrect, is higher for African Americans than for white people. So that was that article. And these caused a big stir. They've really increased the awareness of AI fairness. And so people are really interested in saying, well, how do I know if my algorithm is fair? So one thing that people do commonly is they try to measure what they call fairness metrics. So this is fairly simple. You kind of you just look at your model, split it by group, say men and women, and then you measure various things within those groups and compare them. You might say the accuracy. Is the accuracy higher for one group or another? You might look at the outcomes. You say, is one group much more likely to get a high risk versus another group? And you might look at things like confusion metrics, which might be like false positives and false negatives. So you're more likely to under rate someone with respect to risk. So those are kind of common things people measure. And the key thing is you divide your population into the groups, and then you measure something, and you ideally measure many things. So kind of to get some intuition of what I'm going to talk about, this is a very simple little demonstration. So you got three people. The guy on the right has a high credit score, long employment, high salary. Middle person has medium, high credit score, shortish employment, medium salary. And the person on the right has a lower salary, pretty much low credit score and not a long job history. So if you built a model which is aimed at predicting, like, what's the probability that someone's going to default, say, on a loan, what do you expect? Which person has the highest probability and the lowest? And this isn't really a trick question. So I'll just tell you the answer.
The lower credit score.
Yeah, the lower credit score more likely to default. So this is not like a trick question. So, say a model might come up with like a probability score which isn't something like this. This is totally made up. But the person on the right's high, the person on the left is low. Then there's something in the middle. So just with your intuition, which person do you think which case has the highest error? Like, which one would you predict to have the highest error rate, the lowest accuracy, in which kind of group of people, if you sort of had people in these three categories?
The middle ground?
The middle group. Yeah, it's just like your intuition. On the left side, you're kind of like, yeah, I'm pretty sure this guy's not going to default. He's got everything together. On the right side, you're like, I'm pretty sure he's going to default. In the middle, you're not sure. So when you're not sure, you have higher error rates. And so your false positives and false negatives might kind of look like this. So it's really a very simple concept. When age comes in to play with this, it's interesting because age really is correlated with a lot of things, especially like your likelihood of leaving a job, your credit score, your income. All these things are correlated with age. And in the United States, or in my data, I found this in my data, but then I'm using this public data for this demonstration because I don't want to use Paychex data. In the US, for instance, like, there's radically different age profiles among ethnic groups. So I'm going to show, so my Python code will show how you pull this data and make these plots. So that's kind of what I'm going to show you today, among other things. But these are kind of just age distributions for the US as of like 2019. And you can kind of see, like, on the bottom left, the white, not Hispanic or Latino group, they have this big hump, kind of the baby boomer generation, which isn't really present to the same degree in other groups. Groups like Hispanic or Latino, like, they have, many more people at the young end of the spectrum. So anything that's affected by age, you've got people with very different age distributions. And it's, that some of them might be, so, imagine you're going to say, just predict retirement. Even, you're pretty sure someone 90 years old is retired. You're pretty sure someone who's 18 isn't. Where you're not sure, where your error rates are high, is going to be in like that middle, maybe like 50, 60. Those are going to be where you're not sure. So you'd expect higher error rates, for, say, the white alone population, because they've got that big hump. Kind of, they've got a lot of populations sort of in the middle. Whereas Hispanic or Latino, they're very young, the error rates might be lower for that kind of model. So you can just kind of, with your intuition, say that this is true. The reason it's important is that it's very, very rare that people do anything to try to correct their error metric, their fairness metrics for age. And so you don't know if you'll see differences among groups, whether it's because of age or something else. So that was what my blog post was about. And so what I did is I simulated a process, which is just dependent on age, but not race and ethnicity. I took random populations I just used two groups to make it real simple. The kind of an old and young group, the white alone, not Hispanic or Latino group is old, the Hispanic or Latino group is young. So you know, to kind of compare. So this process doesn't depend on race, but it depends on age. Or it doesn't depend on race or ethnicity, and it depends on age. So even though it's independent, you still see radically different error rates per group. So this is showing false positive, false negative accuracy. And what my post also shows is that if you kind of stratify by age, you can see the metrics become more equal, and it kind of helps you compare the groups a little bit better. But it's fairly hard to get around this, and so it's something definitely you need to keep in mind. Or I think it's important to keep in mind anytime you're looking at fairness metrics. So that's kind of the whole point of what I'm doing. I told you exactly what the code is going to do. So hopefully now we can look at the code. So the code has these different parts. So, and if there's any part, I probably won't, I'm just going to stop after an hour. I don't want to keep you guys long, and you know, I probably can't be kept that long either, because I got very young kids running around. But I'm going to go through census data import and cleaning and processing. It's not really cleaning, it's more just processing. It does calculation and visualization of those age distributions, the simulation of that process, like the simulation of data that gives you that age dependent process, fitting of that data to a model, and then calculation of fairness metrics. So if there's anything in particular people want to see, can let me know. So that's the presentation part.
Maybe we can do a part 2 if we don't get to it all.
Yeah, if you're interested, if people are interested. So this is all a Jupyter notebook. Let's see if I can make this bigger. So hopefully everyone can see it okay. Is it more or less legible?
It is for me.
Okay. So let's see if I can actually click in there. Okay, it's a little bit laggy. Okay, so I guess I'll just talk about the packages I use real quickly. Pandas and NumPy are very common for data manipulation. The census data package is one thing I'm going to show you how you pull data from that package. Then there's a bunch of things, regular expressions, and related to graphing. Some interpolation, which is necessary to convert census data from big buckets to small buckets. And this is for simulation of that age-dependent process. Math is, again, these are for the simulations. I do some things with the file system, saving graphs and things like that. Need random. This is actually to kind of make a nice histogram, and text wrap in the plots. Those categories like white alone, not Hispanic or Latino, that's a long string. And to make that look pretty in a plot, you have to have, do something like a text wrap. So those are the packages. I ran everything already. So I used to have a your path here. That's the only thing I've changed so far in this code, so from what's on GitHub. But it saves some graphs. So I just, give a local local directory where you can save them, anything on your file system. So now census data. So I'm using the census data package, which has both the American Community Survey data and the census data. And it doesn't yet have 2020 census data. There are other packages related to census that also haven't been updated with that data. And I think that data is going to be quite different. So really the most recent data you can get out there is 2019. I did all this work about a year ago. So still the 2019 data is the most recent. And of course that's pre-pandemic, but the population shouldn't change a whole lot. So I should correct this. So I'm using these B01001 tables. And one way, and it took me a while to figure out what tables I wanted to use. I wanted categories where they were mutually exclusive. I didn't want to have, double counts, and race and ethnicity are separate concepts. So sometimes these tables, and people can be more than one race, and sometimes they'll be counted in multiple columns. So I wanted mutually exclusive categories. So I went with the American Community Survey tables, which have these numbers. And to find that's kind of a thing, if you're not used to working with census data. This package has some tools that help you, like it's got a search. So you can search, like the American Community Survey in a certain year for concept and say race. And so if I run this little code snippet, it'll tell you all the tables that you need. And these are the columns actually. And this is the table, the underscore, and then there's the columns in the table. And so you can kind of browse this. It's quite long. And you can kind of decide to see if this table might work for you. And then what you need to do is you need to Google the table and actually read the definitions on the census website to make sure that it's what you expect. But that's kind of how I found these tables. I actually don't work with census data a whole lot. I was mostly interested in this issue for paychecks data. But here I made this list. So each table is one different racial or ethnic group, and its population counts by age buckets for those groups. And I'll show you that data in a second. So now I've gotten that. So this package, there's the tables that have the data, and then there's the metadata. And the metadata is very important. This is kind of the metadata here. It tells you the column and the definition of it, and what it is with these categories. So I want to pull this metadata so I will be able to interpret the data I get. So I'm pulling the metadata. Some of you are familiar, I'm sure everyone's familiar with these Lambda functions. So I'm actually going to just apply this kind of map to this table, to this list of tables. And each table, I'm going to pull the census data and put it into a data frame. I'm pulling the 2019 American Community Survey data, and then I'm going to concatenate them all into one data frame. I'm going to transpose it, and then I'm going to rename the columns, and then I'll show you what that looks like. So this is kind of just what this package gives you. And the package I forgot to say, which I think is important, it's actually just a wrapper around APIs that the census puts out. So it's actually interacting with the census website. So here we are. So we got a variable, the label, the concept, and the type. So you can see, so what I want to look at, age and race and ethnicity. So, I want the information I want. This one's, the sex by age part, that's the same for everything. I don't care about that, but I want the string that describes the racial ethnic group. I want to know, like, if it's male and the age range. So you got the total, the male total. If you do more, I guess I'll do like this. Then you can see eventually you'll get to females. So these are all the different columns, and I want to be able to interpret this, but I don't want this string with all these exclamation points in it. I want the information out of the strings I want. So when I made this, I made a copy here because when I was doing this the first time, I had a heck of a time. I think it was actually just my internet connection, the census API was slow. So what I'm going to do is, the first thing I'm going to do is I'm going to take this column that has the race and ethnicity in it, and I want to get rid of that sex by age part. So I'm going to copy the table, and I'm just going to try to. So this is all very simple, but I'll go through it for people who might be. I'm not sure what the right level is, but I'm going to split this string, and I'm going to take away the parentheses. And I realized when I did this, there's so many things I would do differently. So feel free to chime in. So I'll just make this small, but you can kind of see what it does. So now, oops, I didn't copy the right thing. This is the new one. So now I have this string, which describes the race and ethnicity category, which is what I want. I dropped the other stuff, and this is long enough already. Then I'm going to parse the label. I won't dwell on this. I actually realized that, for whatever reason, I put brackets here, and I shouldn't have. And then I want to change this all. I'll leave it for now, but I don't know why I did that, but it's actually, you don't need the brackets. It's actually going to change that. So, but I'm parsing. So I guess I'll have to try to go through the code. So again, I'm splitting the string on tokens, which I put in kind of wrong, and then I'm going to take certain values. So then if that's one thing that I definitely, regular expressions are something I Google every time. So that is something that I would love to just know someday. So here I'm splitting it. So now I've got a sex and an age group. I'm going to combine the sex categories later. I don't care about that for this project, but then I've got the age group, the string. So I've extracted that from this. at this point. And I'm going to drop, at this point, I'm going to drop the ones that don't have a sex or age group. Because those are total columns. I don't want to include those. So I'm going to do that. And then I've got the head of the table. So very simple. But now I still don't have what I want, because under 5 years, 5 to 9 years, 18 and 19 years, these are all just strings. They don't mean anything. I want numbers. So I've got to parse those strings. And, they come in these different formats. So there's under X years, all the way up. If I make this bigger, the highest category is 85 years and over. So I've got to kind of handle all those cases. And what I want is for each of these fields, I want a range of ages. So I make these little subtables. So this one is going to be for the first category. So, the min is 0 to 4. So it's under X years, so it's 0. Under 5 years is 0 to 4. And so this regular expression. So this is filling it in. We're going to find age max and put in, it's got to be some number from 0 to 9. And I'm only counting one, I guess, one, this can't be 10. It's not that flexible. Hopefully that stays something that's, I don't know if these categories change frequently, actually. That's why I did this. Otherwise, you could have maybe hard-coded it. I didn't really like that as a solution. So when I set the min age to 0, obviously that is the minimum age. The highest age group, something years and over. Oh, actually, this could be more than one digit. And I'm making the highest age max 99, which is for plotting. And it also has to do with when I pull it distribution. So then for those categories, I'm finding that I'm getting that 85 number. And for a lot of them, they're ranges. So like the range, the age of X of something to something, then you get a lot of, you get most of the categories. There's still one missing though, because there's 18 and 19 years. So that was something else. So I had to do that separately. And then I combine all of these. So I actually have, I'll copy this and so finally at this point, you've got these ranges. And now I still don't have census data, I just have metadata. So I don't know if this is of interest to people, if I'm going too slow or too fast. This is kind of what you have to do to work with the census data. I convert some fields to categorical. So categorical variables, they are levels. So under the hood, they're coded as integers, but they have, so I'm converting these strings to integers, which display as strings. And race ethnicity is an age group. This age group are converted to categoricals. That would generally make the data smaller. In this case, the data is not that big, but I do it anyway. So now I'm going to pull the actual data. So census data.download. They have different geographies. I'm going to choose all of the US. And I'm just choosing the variables that are in this table only, because I don't want the total fields. I'm going to get all the variables that I've parsed already. And this is what that looks like. These are counts of people. And so obviously, if you just pull this data, this is not easy to, you want that metadata. B or B underscore. Now, what is that? What does that mean? So I'm going to join up that metadata. Well, first I'm going to transpose it. I'm transposing that this data frame. So the transpose. These are all pandas. I'm converting it to integer and resetting the index. So I don't really want any sort of index there. So I've got a variable and a count. And so now I'm going to join the metadata. So I'm using a merge. I'm merging it on variable. I called variable this string. And I'm taking certain fields from my metadata. I don't want it all. And so at this point, I'm kind of getting there. Now I'm going to actually have census data that makes that you can start to use. At this point, things are feeling better. I've got this many people of this race and ethnicity in this age range. So I've got data. I don't care about the sex categories. So I'm actually going to aggregate them out. So I'm grouping by the race, ethnicity, and age group. And I'm going to sum the counts. And then the ranges I have, I could have joined after I did this aggregation. Well, I guess I couldn't have because I didn't have this this sex field at that point. So but I could join again, but I'm just going to take the first value because it's all the same. And then you've got this. So now I've taken sex out, and now I've gotten just the counts. One thing you'll notice here is that, at this point, it's still hard to interpret these numbers because under 5 years, well, that's 5 years. Okay, that's okay. But this 15 to 17 years, that's only a 3-year time frame. This is a 2-year time frame. So if you want to know, which group has most, are there more young people or old people in this group? It's really hard to interpret these buckets that are different widths. And I prefer for my simulation to have 1 year resolution, which the census doesn't give you. So from here, that's what I'm going to accomplish. This is just a check. I just checked whether that I had all 8 racial and ethnic groups and all the categories, and I do. So now I want to interpolate. I want to take these numbers and get them to 1 year resolution, so I can actually see which ages have the most people in them. So I copy it again. I think I was just trying to avoid pulling census data because I was having trouble with the internet when I wrote this. So what I'm doing, this is very simple. I'm taking the midpoint of these buckets. First just going to find the midpoint of the bucket. So 0 to 4, that's like 3-ish, 2-ish, 2-ish. So I'm getting a midpoint. The width of the bucket in years, so the max minus the min plus 1, so that 0 to 4 would be 5 years. And then I'm going to scale the counts, by the width. And then that'll kind of give me more of an idea of the sort of normalized counts in those buckets. So now you can kind of start to compare, 18 and 19 is somewhat higher than 15 to 17. So now I've done that, right? Now I want 1 year resolution. So I want to interpolate. What I'm going to do is I'm basically going to plot or virtually plot these points, the count scale versus the midpoint. And then I'm going to interpolate that. I'm writing a function to interpolate. So data to interpolate, and it's going to take the data. So the way this works is you get a series of X values and you tell it what X values you want. So I'm kind of taking the full range in 1 year. I want 1 year resolution. So here's, this is basically 99 minus 0 plus 1. I've got 100 points. And I'm going from 0 to 99. And remember, I forced the max age to be 99. So I'm kind of fudging that very upper end. There's this interp1d from SciPy. This is what it will do, the interpolation. This function returns a function. So I'm telling it that I want to interpolate this data, this X and Y data. I want to do a certain kind of interpolation, and it's going to extrapolate between points. And then I can apply that function to these X values. And then I'll get a series of X and Y values that contain the interpolation. So that's what that one does. And so what I'm going to do is I want to do this within each group, racial and ethnic group. So I'm going to group by and apply that function and then reset the index. I often reset the index, I sometimes have trouble with indices. I'm not even sure if I always have to. Something I often just put in there. I don't know if other people do that or if it's something I should pay more attention to. This will add a column. Actually, there's a better way to do this. You can tell it not to add this with an option to apply. I can't really have the option right now. But instead, I just drop it explicitly. I wonder if it will tell me if I kind of. I don't know if it will auto show here. I don't think it will. Okay, write it down. Name of that option. So I know now that there is an option to apply that would just not add this column. It kind of gives you an abstracted column for your groups. So I'll show what this looks like when it's all done. And so I dropped that extra column it adds. I'll show you what this looks like. So I've got the race ethnicity, I've got like age in 1 year increments, and I've got a count that's interpolated. Right. And so then what I do here is I'm actually going to normalize it. So I'm going to, instead of having counts, I'm going to have a probability or kind of a distribution. So sort of the percent of people within each category. And now I'm going to pivot the data table so that I get you can see it already what it does here. So I'll run it again anyway. That it actually pivots so that each racial ethnic group is a column now. And now I can plot this. So before I plot this, let me try it. I wrote some little snippets before this this kind of shows what, oops. So this shows just when you plot the raw data, like when I have the midpoint and that the counts divided by the width of the interval. That's what it looks like. So, and then hopefully I've smoothed over that. So this is just that first category, Black African American. So you can see what it looks like once it's interpolated. So here we're going to plot. I don't think I'll go through the plot code, but the things I want to have some color. So there's this color palette. So I got I'm enumerating over columns. So I'm going to iterate over the columns and add a plot. And each one I'm going to have a different color of the graph. So I thought this was nice. Not anything else that's really notable here. I think the text, I don't think there's no text drop yet. This just makes those plots. And so you can see this shape that's interpolated in 1 year. It's kind of like this, but smoothed. So it's approximate. This is approximate 1 year intervals. So I didn't do this just to make the plots, although for me, just looking at the plots really makes me think about how this would affect my fairness metrics, what it means for what I'm measuring. But I want these distributions because I'm going to draw random samples of people from these distributions. And so I want to sort of simulate a case where this is the population and you're looking at different at groups of people that sort of have these characteristics. So again, there's what it looks like. And now I'm going to only do 2 groups because I want to, the point of my blog is just to look at, to kind of compare fairness metrics and just kind of demonstrate that age can affect them. So I just choose a young group and an old group. So you can see the difference. This has got this big peak around 60. This the highest population is teens really. So these are extremely different age distributions. And I replotted this because this is what I put on my blog. I use the colorful one for a lot of presentations. So now I'm going to start drawing random populations. So I want only those 2 groups. So I've got this SN. I'm selecting certain groups. So I'm going to take the population where the race and ethnicity is one of these 2 that is in, and then I want the over 18 population. I didn't really have to choose over 18 population, but it was kind of related to my work with the labor market where most people are over 18. So I was personally more interested in that. So I'm going to limit my data to that. And then I'm going to draw a random sample from the distribution. So what I'm going to do is for each group, I'm going to just draw people. I'm just going to randomly, I'm going to make a table of people and assign them an age randomly based on the probabilities that are in these curves. And so it's pretty simple. I'm just here's something I'm handling nulls, but I'm just going to sample some number of cases with some weight, which has a weight variable, which I have as count weight in that table, and I'm sampling with replacement. Which, so then I'm just gonna get my populations. So for each, I'm gonna get 5,000 each of both groups, the white, alone, non-Hispanic, or Latino, Hispanic, or Latino groups. And so just randomly, if I draw a random person from that distribution, the first one I draw is 53 years old, the second one is 94, the third one. So this is kind of what it looks like. And so I've drawn 5,000 of each. And I'm just kind of showing that the curves that I do of the population I drew more or less kind of somewhat look like the population I'm drawing from. Just kind of a sanity check there. So this is a histogram, very simple histogram. So I'm going to plot that, the age of the histogram with my, and I'm going to do 2 plots by race ethnicity. And I also, as a sanity check, I'm showing the means of my population. So you can see that it's about 10 years older, which is a big difference for some things. So now that I have these random people, I'm going to give them a random response. So I'm going to simulate some process. It could be anything. It could be something related to health, like your probability of having lung cancer. Or it could be the probability of being retired. It's just going to be something that depends. It's completely random, and then also depends on age. So I have 2 random things. One is a feature that I'm going to model, and the other is a bit of noise I put on top of that, so that my model isn't perfect. So what I'm going to simulate is basically y goes, the response is x plus age with this noise attached. So first I just give these people these random factors, x, which is completely random. It doesn't depend on race or ethnicity. So it's just, it'll just be the distribution of data across groups should be the same. Same with the eta. So now I'm going to add age to this model, and I'm going to get my linear equation, which looks like this. So I'm actually going to simulate a binary process, yes, no, using binomial distribution. But first, I'm just going to do the part that goes in that contributes to that the probability. I'm going to get the probability that you put into that binomial. I'll show you what that looks like. So now I've just improved age, and I've got myself this. Not. I managed to get this inconsistent. Okay, so yeah, I've got this linear. So this is related to like when the probability will be the the x-bit function of this. That's kind of simulating a binomial process, a binary process. So then I'm going to get a probability out of this. So now, given this person is 94, the probability of whatever that you're simulating is 96. This person is 3%. It's depending on age and this random factor. So now I've simulated that process that depends on age. Well, I've gotten the probability. I haven't simulated it yet. So I want to make sure that it kind of makes sense. And I'm also kind of looking at the average across groups. So the average of the probabilities, you can see is lower, is higher for the older age group, as you would expect. This is sort of averaging, I'm aggregating on the mean probability. This would sort of be like the fraction of people you expect to have their outcome that you're looking at, a yes, no outcome. I plot that as well, just to kind of show what it looks like. So you can see that because of the larger age population, you've got kind of the second, bimodal distribution, whereas most of the Hispanic or Latino, it's have low probability. So now I'm going to say, I don't want a probability. I want a yes or no answer. This is kind of what you get if you have data. They either had something or they didn't. They either retired or they didn't. So I'm applying this function using a binomial. Luckily, NumPy gives you all this. You can just kind of give it this probability. And then you can actually just simulate the process. So I'm going to get an answer, like say, if my probability is 75%, I'm going to simulate that with a random give it that probability, 75% chance I've got heads, 25% chance tails. I'll do that for every person in my population. And so what I'll do here is I'll show you what that thing looks like. Let me know if there's any questions. So you can see, like this one has a low probability, but yet they get, because there's some probability, they still get a 1. They still are a target. This one high probability, a target. This one 0. So using the probabilities, and with the lower probability, you're more likely to get a 0, but sometimes you get a 1. So I'm simulating what you'd see in data. And so if you had real data, you wouldn't have any of this part. You'd have this target status. You'd have maybe the race, the age, and the target status. That would be what you have in your data set. And from there, you want to fit that to something. Then you have X, because X is a feature I'm assuming I'm going to fit to. So I had age, and X, and a target status. And that's often what you would model, something like that for machine learning. So I'm doing the target status, the mean target status. It looks very much like the mean probability. So that's a good sanity check. So now I'm going to model. So I've simulated a process. I'm going to fit it. And I'm fitting it to 2 models. And I really only talk about one. I talked about one earlier. I'm also going to leave out age and fit it. So the model that generated the data is y is equal to x plus age. So that should be a perfect model. I expect it to be, I expect I'm going to get out what I put in. If I don't, I'm in trouble. So I'm taking my x for one model, my x for another model, my target status using sklearn. And I'm just going to, so this is a simple linear model. And you could fit anything to this. You could fit, a random force, etc. But this is actually the best thing to fit to it because it's such a simple process. And I know ahead of time exactly that this is the perfect model for this. This is the process that generated it. So I'm fitting both of them. So I'm getting 2 fits. I'm going to fit age, I'm going to fit X. So this is actually just doing the fit. I'm going to look at the coefficient. So I haven't yet done my prediction. I'm just fitting the model here. So this is doing the model fit and doing the coefficients. So this is kind of what I put in. I didn't actually show that, but I had X near 1 and age like at 0.1. So this first model is exactly, I've gotten out the coefficients I put in. I save it. I don't know why. I guess I thought I might want it later. And now I'm going to predict. I'm going to make and add columns to my data frame. I'm going to predict the probability for the X of the age model with age, without. And then I'm going to get a target status with and without age. And so this is what I get. So, I've got my actual target status and then I got my prediction. So you can see that because of the noise, they don't always match up. So I guess the X age model is the more interesting one. This guy has a low probability. My target status, I predicted a 0, which you kind of expect from the underlying probability, but there's randomness in that. And this is a 1. So you can see that. So I have my real data, I have my predictions. So I can see how accurate my predictions are at this point. I just showed my boundaries. So, that if I between 0 and 50%, I predicted 0. And this is for the model probabilities, not the input probabilities, but the model probabilities. So it's kind of what you expect. And here's a crosstab, pandas crosstab. We kind of plot 2 columns. And here actually 2 or more columns. I've got 2 different. I'm looking at 2 different. Like I've got the target. I've got for each ethnic group. I'm looking at the confusion matrix. So, there's people who are predicted, who are a target and are predicted to be a target, are not and are predicted not. So the cross terms are the accurate ones. The mistakes are on the off diagonals. So you can kind of see the confusion matrix. And the reason that there's mistakes for this target X and age one is because of the noise factor. Otherwise, and the randomness. So, it's intrinsically a random process too. But those 2 things are what make the noise that you actually have errors in this, despite the fact you're fitting a perfect model. This is as perfect as you can get. So this is the other model that doesn't have age in it. You can see it's less accurate. You got more off diagonals. And that's what you expect because you're leaving out that important information. So I want to just here, maybe I'll skip this part. I won't go through this in great detail, but I want to actually plot the the distribution of probabilities from the model. So you can see for the two different groups. So for Hispanic or Latino, this is many more people with a very low probability of whatever your outcome here is, whereas the white alone non-Hispanic or Latino population has a fair number of people with a high probability. If you look at the model, it has just age, that it doesn't have age, it has just like that X feature. The model probabilities, they're the same for the two groups because it can't distinguish them. It doesn't know that one is older than the other. And that's actually why it's wrong. So without age, the model is much worse. And so I do the same thing for the actual, like estimating sort of the actual distribution from the underlying process. So it's very similar to this, pretty much identical, which is what I want. All of that's kind of sanity checking. So now I'm going to do fairness metrics. So I have a model. I have data where I know what my answer should be. And I have a model, and I'm going to calculate the fairness metrics and just demonstrate that they're different across the racial and ethnic groups, despite the fact that the underlying process has nothing to do with race or ethnicity. So I define some functions to get some common metrics, like the false positive rate. And the denominator is 0. I'm going to make sure I don't fail out. But this is for people who are not, in reality, they're not, they don't have the outcome. They're not targets. So what percentage of them are falsely just positive, false negative rate, and accuracy. And I won't go through this in detail. I'm just going to calculate these metrics. Each of these take in the data and the model target column because I want to do it for both models potentially. And I'm just going to calculate these metrics and have it so that they fail out. But try and accept where if there's something like the denominator is 0 for some reason, it's not going to blow up my code. It'll just kind of give you a null. So my overall false positive rate, I'm applying this function. I got 10% false positives for everybody. But how does that go? If you look at different racial and ethnic groups, how does that work? And I'm using this apply again. I'm going to apply this function to this group. Within which racial ethnic group, I'm going to apply this function, and then I'm going to reset the index. And so then I can look at, then I'm just basically calculating my metrics within each group. So overall it's 10%. I do equal 5,000 each, so you kind of expect it to split the middle. And you can see, the false positive rate is almost twice as high for the white alone, not Hispanic or Latino. And, this makes sense. You've got, this group has a lot more people, especially false positives that are, kind of in the middle older category. And so I'm going to add all those metrics to the data frame. That's just one example. I'm going to do them all here. So this is kind of, I apply the false positive, false negative. I do it for both models. I think ideally I would have had a long form and not had separate columns. But, or maybe I did, let's see. Yeah, first, so I do it for each model, and then I concatenate them. So then I have, like accuracy. So here we go, accuracy by group. It's kind of similar for the two. Accuracy tends to be less different than the individual, like, often accuracy can be similar across groups, whereas your individual error rates are very different. Like the false negative rate is much higher for Hispanic or Latino, false positive for white alone, not Hispanic or Latino. For the model that doesn't include age, it's kind of interesting. We just got this really high false negative rate because it's just a pretty terrible model. So in some ways it looks more equal. In some ways, like these metrics, it looks more equal. The accuracy is maybe a bit more different, but it's actually because the model is so terrible that you can't really distinguish the differences. So this model, the model with age, where you have more, it may look more unfair, you've got more differences across groups, is the model that's correct because of the underlying process. So if you just look at these metrics across groups, you might draw the conclusion that maybe the model is discriminating against one group or another, and that it's due to race or an ethnicity. But obviously this process is because of age. So that's what I wanted to demonstrate. So that's basically what I wanted to do. So the other thing I did is I stratified those metrics by age to kind of show that that kind of takes away some of the differences. I won't go through that in great detail. So I actually kind of got through this. So, you can see that the rates become more similar as you, and like in these load categories, like, there's basically everyone's, the false negative rate is one, because anyone who's negative is wrong, because they're so young. If you look at a more the middle category, it's more interesting maybe, but you can see the numbers become more similar. And just doing the stratification, seeing that numbers become more similar, you know that you've got something that's happening due to age. And so you definitely want to take that into account when you're assessing fairness. I did different finer grain buckets. And I won't go through that because I think I've gotten through the major part of my code. I guess one thing I'll do is the calibration plots. And I realized I had an error in my calibration plots. Where are my calibration plots? Right down here. So calibration is kind of just, you want to say how your model risk tracks your actual risk. And so what you want to, this is usually done by plots. So like this first plot. So I realized that this was, I did make an error here. So I'll show these ones. But so ideally you want, if your model probability is 40%, you want people who have probabilities around there to have an actual rate around 40%. So you have to bucket, because you don't have a rate here. You have like target test 1 to 0. So you have to look at groups of people. And so people if the mean of some group of people's probability is around 40%, you want the model to give you 40%. This never would happen in reality. You'd have some sort of function that would hopefully monotonically increase, but wouldn't actually like be this nice straight lines, because like my model's so perfect here. It never ever happened in real life. But you can see the calibration plot shows that the two groups are similar. If you leave age out, then your model probability, because you don't know about age, it's going to predict the same thing across the two groups when it shouldn't. It doesn't know that that people are 30%, this particular group of people is much younger than the other, they have a different response. So you can see the two lines diverge, and that's a sign that you're missing something in your model. So I won't go through the code, but I have these things to plot these. All right, so that's basically this project. Is there anything anyone wants to like talk about or tell me to do differently or need more information about? I think I see somebody. I can't see everybody, so you might have to just talk because I can only see like one person.
How much time did you spend planning and figuring out what you needed to do before you actually started coding?
So
it's so complex.
Yeah, well, so this came from my work because I do labor market stuff. So, and that's what I'm doing in the labor market and in any subpopulation. Often, even if the census data would tell you they're similar, like your population is different. Like in the labor market, like men and women, the age distribution isn't so different. But like if you look at a particular industry, like, especially in fields that historically might have not had a lot of women, like women skew younger. So I noticed in my data, like that I saw all these difference in ages. And I was looking at rates of people quitting their jobs. And you just kind of know that older people are more stable, in their jobs. Like, or, you kind of know from your own, like life path that, like when you're 20, that's not the job you're going to have for 10 years, So just looking at those age distributions, I kind of knew there'd be a correlation. And I got worried about it for my own data. So that's kind of what happened. So I explored it at work, and then I have a blog, and it's I just wanted to kind of share it with the world through my blog and see what people might say. No one's really said anything on my blog, but my blog is kind of aimed. I sort of hope someday someone will say something. At Paychecks, we have kind of a small group, and not a lot of people do this kind of work. So I don't have like a lot of people to bounce ideas off of. I don't know if I'm answering your question. I'm going on and on, but I guess the answer is probably a long time because I did it at work first, then I did it through my blog, and I kind of am learning Python or relearning Python. Everything was done originally in R. So, and then I did a long time, longer than you would think, probably. So, any other questions?
You said you did this in R first at work, and then for your blog, you rewrote it in Python?
Well, it's obviously different because I didn't do census data. At work, I have our own data. So it's a completely different, and the model's completely different. I'm like looking at a XGBoost model, it's totally different. But the basic principle, and I wanted to show it with census data because that's like the most basic thing. This kind of shows that this would be a general problem for most projects. So yeah, that was one of the biggest hurdles for this. Actually, the thing that took the longest was figuring out how to pull that census data. I knew census data existed, and then I found these nice packages, but it's still like it's just they don't make it. I mean, those fields are just. It took me a while to find the right table, and then to figure out exactly what I needed to make sure it was right, and then figure out like how to get those column names and things.
You put your blog address up again?
Yes, and it's on the like the meetup. So
Okay. Don't worry about it then.
Yeah, and the code. So the code. Okay, and there's one I want to fix it, but if you go there now, there is one error in the code. Like there's a lot of things that are done inelegantly, but there's one actual error. It's in the calibration part. I actually put the wrong thing in this. There's two different calibration plots that are done. So this one should say, this should be actual prob instead of model prob that I'm plotting. So, oops. I won't do it now because I just lost it. So that's an actual error in this, I realized when I was preparing this talk. Let's see if I can actually do it now. So yeah, now this is gonna be right. So you see these shouldn't lie on top of each other. And they don't if I do it right. So if you pull the code, there's that error. There might be other errors. That's the error I'm aware of. So Josh, sorry, any other questions? I noticed that Josh has George's picture. That's kind of throwing me off.
George lends me his account because he has a paid Zoom account. We use it as a community account so we can record sessions.
Well, I kept thinking, oh, George is here. Nope.
Yeah, sometimes I'll put my name as not George.
Cool. So I don't know if there's more questions or if anyone has comments. Like, was this a good level? Was it kind of too hard? I went too fast. It's hard to know how fast to go.
No,
I really enjoyed it. Sorry, Mitch, I didn't mean to talk over you.
Sorry?
Sorry, Mitch, I didn't mean to talk over you.
No, I was just saying it. I think it was just the right level, about the right speed.
Cool. Yeah, this was kind of my first blog written with Python. My other blogs with R, and I have to do both. So now when I read my code now, I'm like, man, I could have done some things differently. I don't know what are the things that make Python like. What are the biggest things like when you're writing Python that make it like, I guess, right? Is it those iterators? Is it
for me, like a lot of the list handling, slicing, the just kind of the way that that syntax, and yes, the not the constructors, but the list construction syntax. I forget what the name of that is, but it just makes things very concise. And when you understand the syntax, it's pretty intuitive.
And I'm never completely sure the style too. So, like, how do you do comments? What's the best? Is it? I guess that's different with Jupyter, which I'm not a huge fan.
List composition, I think, is the term.
Mm-hmm. Yeah, like X for X in.
Yeah, that stuff.
That kind of thing. Yeah, like here's one.
Yep, you got it.
That part I know about. That part I can kind of do. This is just converting obviously the labels to a string. Oh, I didn't go over the text wrap because that was super handy. Like these long names, I had to wrap them in some of these plots that have a legend here. They wrap. I mean, when they didn't wrap, the plots looked awful. And for me, being in data science, I like to make the plots look pretty. And that's one of the things.
Yeah, no, it's the little things like that that really make a difference.
Yeah. And it's sometimes so hard. Like I'll spend 20 minutes on Stack Overflow, like looking like, how the heck do I do this?
Yeah.
Yeah. when I was coding, I had like 50 billion Stack Overflows, you know, of course. That's how I do my Python. Awesome. Well, thank you.
In your group at Paychecks, you use both R and Python?
Yeah, well, traditionally we're all R, and now
what do you
everyone's
choose to use R for versus Python?
yeah. So Python we did, or R we did everything in for a while, but now we're moving into Azure. And Azure is very, you know, Azure is like the Microsoft cloud, like AWS or Google Cloud or whatever. And they really have everything really optimized for Python. So it's kind of, and I always liked Python better than R. I really never liked R that much, but I got really good at it doing it, you know, all the time. So now it's kind of much more natural for me. But yeah, now we're moving into Python because of Azure. And so now I do both because I have the old stuff in R, the new stuff in Python, and like my brain is just mushed half the time. Yeah, when I started my job, I stopped kind of coming to this meetup because I had to learn R really well, and I it's hard for me to learn a new language, two new languages at the same time. So, and I didn't do Python for like literally decades yet. Never that much, you know, never so much to really master it. Unfortunately, but maybe that's.
I wouldn't even say that I've mastered it. I use it not infrequently.
Yeah, I guess, or even semi-mastered. Like R, I use every day for years, so now I feel pretty comfortable. So, but now I'm actually going to switch more Python. Python is going to be more my future. So, and that's always the way, isn't it? It's if you learn one thing and then it's, you know, on to the next. Because that's why that makes it more fun.
Once you get comfortable with something, you move on.
Yeah. Yep.
Well, it's good to keep challenging.
Yeah. Well, thank you, everyone.
Thank you. Yes, thank you.
Okay, I'll see you guys next month. Have to see what the topic is.
And don't forget, we have the organizing meetup next week, if you can make it.
Yeah, I should talk about Yep, I'll try.
Awesome.
Okay,
awesome.
cool.
I hope to see you there.
Good seeing you.
Good night.
Good night.